In this video, we'll do some more involved examples in applying the integration by parts formula. In this integral here, I have the integral of x squared times cosine of 2x. A little experience tells me it's a good choice to take u to be x squared. If I do that, I have to take dv to be everything else in the integral, including the differential. So if dv is a differential, it should have dx in it. I now differentiate to find du, it's 2x times dx. And I then integrate to find v. So I have to integrate cosine of 2x. That should be sine of 2x. If I differentiate sine of 2x, I'll get a factor of 2, and I don't want that extra factor of 2 there, so I better divide by 2. And now we can apply the integration by parts formula. It says u times v. That's going to go there. There's v. And then it's going to be minus v du. And du is 2x dx. Let's simplify this expression and reflect on it. I've got 1/2 x squared sine of 2x. And then the 2's cancel here. So I'll have x times sine of 2x. And you want to observe what's happened here. I started with x squared times cosine. I now have x times sine. And at first glance that may or may not seem like much progress, but it usually is good progress if you've reduced the power. And when you've reduced the power like this, if you want to continue to make progress, you need to repeat integration by parts. So we're going to do integration by parts again for this integral. We're going to take the same kind of u. We'll take u to be x and dv to be the sine expression, and then just run the integration by parts formula again. So u will be x. If I differentiate it, the derivative will be 1, so du is equal to dx. dv has to be everything else in the integral, including the differential. I need to integrate sine. If I integrate sine, it's going to be minus cosine of the same thing, and I don't want the factor of 2 that the chain rule would give me, so I divide by 2. Notice the minus sign and the dividing by 2. We're then going to rewrite the first term here. So that's just rewritten, and then I'm going to be minus the integration by parts formula. So it's going to be minus u, which is x, then times v, which is the cosine part with the minus, that's u times v there, minus v du in the integral, so v du in the integral. Notice that I put big brackets here, anticipating the fact that I need to distribute the minus sign here through the integration by parts formula in brackets. We'll clean up the expression next. Notice what happens is the first term will become plus. There are two signs, minus and minus, so it'll be plus 1/2 x times the cosine. The term here is minus, minus, and minus. That's 3 minuses, so it will stay minus, and it will be the integral of cosine. Notice that that's really good progress now because there's no power of x anymore. We've reduced it down to degree 0, and we just have the integral of a cosine. If I integrate cosine, I'll have minus 1/2. I've got to go up to a sine and divide by 2 as we've been doing. And there is our antiderivative, and the only thing left to do is 1/2 times 1/2, that's 1/4. So this is an example of using integration by parts repeatedly in order to reduce a degree of a power of x. In the next example here, we'll use integration by parts repeatedly, but the spirit will be a little bit different. The outcome will be a little bit different. Here I have an exponential times a trigonometric. I'm going to take u to be the exponential. It turns out that you could make the other choice. You could take u to be the trig function, and it would still work just as well as what I'm doing here. But I'm going to take u to be the exponential. I then have to take dv to be everything else in the integral, so I have to take it to be sine of x times dx. To find du, I need to differentiate, so derivative of e to the 2x is 2 times e to the 2x, using the chain rule. And I write it as a differential, so the dx comes over here. To find v, I need to integrate sine, and the integral of sine is minus cosine. If you're confused about when to put the minus and when not, just remember about differentiating. The derivative of cosine is minus sine. We don't want it to be minus sine. We want it to be plus sign, so we put an extra minus in front. We now run the integration by parts formula. It's going to be minus e to the 2x times cosine. I prefer to write the exponential first, so minus cosine times e to the 2x. Then it's going to be minus from the integration by parts formula, and then it's going to be v du. So minus cosine times this exponential part for the differential. Let's clean that up a bit. I've got the first term, and it's going to be plus 2, so I'll put that outside, and then we've got the exponential in front times cosine. Now it doesn't look like we've really made any progress because I've got this integral e to the 2x times sine, and I've replaced it with a problem that now involves e to the 2x times cosine. You've got to imagine that having sine or cosine is about as hard as the original problem. And in fact it is. It doesn't seem like we've made any progress at all. But if you stick with integration by parts and do it again for this integral now, it turns out you will be able to make progress. Something very special will happen. And I'm going to take u, just like I did before, to be e to the 2x again. So the differential is just as we calculated before, but now I'm going to take dv to be the cosine. I integrate cosine to get sine of x. So I've got this exponential times the cosine in front, and then I've got plus 2 times this integral that we're going to apply integration by parts again. So I'm going to put some brackets like before because I'm going to need to distribute that 2 through the integration by parts formula. It's going to be u, which is the exponential, times v, which is sine, and that's going to go there, minus v du. And look at what happens here. I get v du, I get a sine times an exponential, essentially the original integral that we started with. So let's clean up what we have. I'm rewriting the original blue integral again. It's the exponential times sine. And then I'm going to put this expression here over here, but kind of cleaned up a little bit. I've got that first term, and then I'm going to distribute the 2 through the second term there, so 2 times e to the x times sine. And then I'm going to distribute the 2 through this third term, so it'll be minus, notice it'll be times 4 now because of the 2 in the integral, so times 4. And it's e to the 2x times sine of x. I wrote it in blue because that's the original integral. What we're going to do is solve this equation now that I've written for the blue integral. If I have one of them over here and minus 4 of them over here, I will have plus 5 of them when I bring this one over to the other side. On the right side, I will still have just this expression in black, and I'm rewriting that in a different order, but I'm rewriting that. So what's happening here is by integrating by parts twice, I come back to the original blue integral on the right side, and I can use that equation to solve for the integral that we want. I have 5 of them. If I want the integral, I have to divide the right side by 5 to get the integral. So I need to divide the answer by 5. Now when we're combining, there's a formula for the antiderivative. There really should be a plus c in there. The plus c is coming into the expression when I'm combining two antiderivatives. They're really not equal quantities. They could vary by a different by a different constant. So this symbol here and this symbol here means an antiderivative of this function, and there are lots of antiderivatives that differ by different constants. We should respect that by putting plus c here.